Alright, hi everybody. So today I'm going to talk to you about acid-base equilibrium problems. So far in acids and bases, let's just recap what we've done really quickly. We've talked about different definitions, Arrhenius, Bronsted-Lowry. We talked about weak versus strong acids and bases. We talked about the properties of acids and bases, meaning what general characteristics they have. And then we've also spoken about how to find pH, pOH, H+, OH- of strong acids and strong bases. Now, what happens if you were to have a weak acid and they don't dissociate completely? I think pretty much everybody at this point is clear that if you're a strong acid or base, you dissociate completely. But if you're a weak acid, you don't dissociate completely. And so here I'm going to do some examples where you have a weak acid and how to figure out the pH of them, or how to figure out the H+, or how to figure out what's known as the Ka. Now, when a weak acid dissociates, it doesn't dissociate completely. And so one type of problem that they'll be asking you about is, well, what's the Ka of the acid? What's its dissociation constant? And by looking at the dissociation constant, it allows us to tell what the acid strength is. The general rule is that the higher the Ka equals the stronger the acid, or the lower the Ka, the weaker the acid. And this is strength over here. So now this first problem that I do uses an acid called phenylacetic acid. This is the stuff, or the acid that builds up in people's blood if they have a condition called phenylketonuria. And this is, a phenylketonuria is, or phenylacetic acid, it's made from phenylalanine, which is found in sweeteners. So, people need to avoid this if they have this phenylketonuria condition. So, I'm going to abbreviate the acid as HPAC, but its real formula is shown here. And what happens is, when I have this acid, I can show you down here, it will react with water, and it will form H3O+ and the anion. And I'm telling you that if you have a 0.12 molar solution of this, its pH is 2.6. So I'm giving you the pH, and I'm telling you what the initial concentration is. Now I wrote an equation down here, and what we can do also is write a Ka for this. This is just like any other K, except A stands for acid. It's the products, so we have H3O+ times PAC- over the reactants, HPAC. Notice I leave out the water. Why do I leave out the water? Anybody know that one? You can tell me in class why we leave out the water. And now what I'm going to do is set up an ice table, which should feel familiar to you. I stands for initial. We have 0.12 molar. And we don't have any of the products yet. We have -x. We have +x, +x. We have 0.12 - x. And then we have x and x. Now the thing is that I'm given the pH, and so I know what x is. Since I know the pH is equal to 2.6, I know that 10 raised to the -2.6 is going to give me the H+. So let's go ahead and let's try and do that now. Take out my calculator. So we're going to have our 10 raised to the, let's do clear because I'm messing this up. So we're going to do 2.6 negative, and we're going to do 10 raised to that. And so we're going to get that our H+, which is equal to our x value over here, is equal to 0.00251 molar. Now this allows me to go through and plug in all those values into the Ka. The Ka we can now solve for is equal to x squared over 0.12 - x. We know x, so it's 0.00251 squared over 0.12 minus 0.00251. So if I square this value here, and then I divide it by parentheses 0.12 minus 0.00251 in parentheses, I will get 5.3 times 10 to the negative fifth. So I should get 5.4 times 10 to the negative fifth. That's my Ka. So this is just an equilibrium problem. But it's an equilibrium problem in which I'm doing this in an aqueous solution. And I have to do a little bit more work because I have to take the pH and make it H plus first before I can go through and solve for it. Now what happens if I give you another example here, where I ask you to find the Ka of NH4 plus. Now I give you a little bit of information in the beginning. I tell you the conjugate acid of NH3 is NH4 plus. It's a weak acid. First thing you're going to do is you're going to write your equation. This is going to react with water. It's going to form NH3 plus H3O plus. Just like I did in the previous example, I can go ahead and write a Ka. Ka is equal to the products over the reactants. Why don't I include the water? You can let me know tomorrow. You can set up a little ice table right beneath this. Save a little time, don't rewrite the reaction. They're saying that this is 2 molar, 0 and 0, minus x, plus x, plus x, x, 2 minus x. Well, they give me the pH again. pH equals 5. H plus then is 10 to the negative fifth. So now I know what my x is. I can plug that in. 10 to the negative fifth over 2 minus 10 to the negative fifth. Now look, this 10 to the negative fifth here, remember that 5% rule, that's a really small value. And I can ignore it. If I want to save a little bit of time, this is 10 to the negative fifth squared. So that would be 10 to the negative 10th divided by 2, and so that would be 5 times 10 to the negative 11th. That will be equal to my Ka. Now what if I'm given a Ka and I want to find the equilibrium concentrations? So if I want to do that, I can show you a problem where we have this acid down here, propanoic acid. And so they want us to find what is the hydronium ion concentration and the pH of a 0.1 molar HBr. And again, I abbreviate this. I could write out the whole acid, but I want to save some time. So I'll do HBr plus water yields H3O plus PR minus. I'll have my Ka equals PR minus H3O plus over HBr. I'll do my ice table, and in my ice table we're going to have 0.1 molar, 0 and 0, minus x plus x plus x, 0.1 minus x, x and x, except now I don't know x. So now my Ka, they're telling me, is 1.3 times 10 to the negative fifth. We don't know x, that's x squared over 0.1 minus x. Again, the x is going to be really small. I can tell that by this tiny little k value over here, 10 to the negative fifth. So what can I do? Well, I can ignore that. So I can have 1.3 times 10 to the negative fifth equals x squared over 0.1. If I solve for x, I'm going to have x equals the square root of 1.3 times 10 to the negative sixth. And if I take the square root of that, so if I do 1.3 e negative 6, and then I do the square root of that, I get that x is equal to 0.00114. Now x is H3O plus, right? Here's my H3O plus, here's my x again. So this is equal to my molarity of my H3O plus, which was one of the things I was asked to find. What is the hydronium ion concentration? I want to find the pH, I can do the negative log of this. So I do the negative log of the H3O plus, and if I do the negative log of that, I get 2.94. All right, there we have it, folks. How to do weak acid problems. They are very repetitive. So you're setting up an ice table. You're either solving for X or you're solving for the Ka. That's really all there is to it. Now look, here's some cyanic acid down here, extremely acrid, unstable substance. And I ask you what's the H3O plus and the pH of the solution. I give you the Ka. You're going to do this one on your own. We're going to go over it tomorrow in class. Next, what we're going to do is talk a little bit about buffer systems, and we'll do that during the next video. We'll talk about indicators, and we'll talk about neutralization reactions and hydrolysis of salts, and then we're done. So thanks for watching.